All right. Hello, I'm Ethan. My project was on mapping several invasive plant species using deep learning in a region in Nepal. So the objective of this project was basically to examine the spread of various invasive plant species and then to analyze the impact that human activity and climate change has on this spread. For this research project, we focused our study on the Chitwan Annapurna landscape in Nepal, just because it was a biodiversity hotspot, so it had a lot of factors that we could look at. Our general approach for this project was to utilize a machine learning algorithm to identify the presence or absence of a specific plant in a satellite image, given like the image data and as well as several like ecological factors such as like temperature, slope, and elevation. And so for this, we trained a deep learning model using multispectral data and survey data that was obtained through collaboration with the Tribhuvan University in Nepal. So the data we were given for this consisted of multispectral satellite data from the Digital Globe Worldview 2 satellite, as well as survey data taken in Nepal. So the multispectral data contained image data over 8 several bands. So and then the survey data taken in Nepal contained various like ecological factors, like I said, like elevation, temperature, and slope, as well as the presence or absence of 7 different plant species. And so what we did was we combined the multispectral image and the presence and absence data from the survey to create a data set of labeled images. And we used this to train a convolutional neural network, which once trained could be used to predict the absence or presence of a specific plant over an entire satellite image. And then once we have those results, we can map it onto satellite images from varying time frames so that we can see the spread of this plant as time goes on. So for this convolutional neural network, we based the initial model off of examples from the Keras documentation, and we just generally improved on it by using our our own data set. Our final model had 4 convolutional layers and 3 fully connected layers. But in training this, we ran into a bunch of challenges. For one, the way that the survey data was taken, they basically had a device that gave them the longitude and latitude points of the point that they were standing at. But what they did was they just kind of looked around to see if this plant was in the area. So there was like, I guess, an error of around like 10 meters of inaccuracy of where the latitude and longitude points pointed to and where the plant actually was. So we had to choose like an image size that took this into account and could correct this. Additionally, the dataset was relatively expensive and focused mainly on roadside areas. So this helped if we were only looking at the spread along the roadside, as we would need less images. But for our model, when we tested it across like the entire image, it was much less accurate in areas that we did not train for, such as like deep forests. And as previously mentioned, we had insufficient data as the plant that we had the most data for, Lantana, we only had 61 points. And of those 61, we only had 14 which showed presence. So we had to introduce a lot of artificial samples through data augmentation techniques so that we could properly train the sample. So our best model was able to relatively consistently get around 95% training accuracy and around 85% validation accuracy. So we used this model to predict Lantana on the Tanahun district, which is the image shown on the left. And then once we got these predictions, we mapped it onto the original image, which is shown on the right, where the green shows the presence of the plant and the red is the absence. And then so now we're currently in the process of obtaining more images and more survey data so that we can evaluate or more accurately evaluate how accurate our model is and then go from there.